Hello everybody, I'm here with another physics video detailing more about current, resistors, especially in regards to circuits. So the first question, our figure shows conventional current passing through a resistor, the arrow showing the direction that the current is flowing, which is correct, and there could be more than one correct choice. So when given a resistor, the key thing to remember is that across the resistor, so across this resistor, there will be a voltage drop. So whatever the voltage was before the resistor, the voltage will be less than that after the resistor. So since voltage is really just electric potential, we know that the electric potential is lower at point B than at point A. So that's one of them. However, even though the voltage drops, the overall current remains the same. So in other words, the current here at A is the same as the current here at B. And then these are the only two, these are the two correct answers. Charges are not moving slower at point B than at point A, because if current is the same, current, I, is a measure of charge over time. So if the charges were moving slower, the current would change, so that one's not true. We already know how option 4, the electric potential is not higher at point B than it is at point A, and we know that it's not the same at point. This next question asks us, when the current through a resistor is increased by a factor of 4, the power dissipated by the resistor does what? And it gives us some options. Again, I've written the equations we're going to use up in the top right here. So the one with power that has to do with resistance and current is this equation right here. So we have power equals I squared R, and it's asking about what happens when we increase the current by a factor of 4. So that means our equation then becomes P equals 4I squared R, or in other words, P equals 16I squared R. So the power dissipated by the resistor increases by a factor of 16. For our next question, we have a 10 amp current. It flows through a wire for 2 minutes. And then we just have the natural definition for the charge of an electron. It's just helpful in this problem, I guess. How much charge has passed through this wire? So we have our current here, we have our time here. This is 2 minutes, so we actually want this to be 120 seconds. It's always good to put things in the standard units that we use. So for time, that is seconds to get us an accurate number. So we use the equation here, I equals charge over time, which we can rearrange. We start with I equals Q over T. We want Q by itself, so we multiply both sides by T. We get I times T equals Q, and that's just 10 times 120. So Q equals 1200 coulombs. And it's really important, again, to make sure that we're doing things in units of seconds, because otherwise this wouldn't be quite accurate. This would be amps per minute, and that does not equal charge, or that doesn't equal coulombs. Charge is just in terms of coulombs, which is amps per second. Our next question asks, what is the voltage drop across a 5 ohm resistor? So that's our R. If the current through it is 5 amps, so that's our I. So it wants the voltage drop, which is V, so this is just Ohm's law. V equals IR, that's up in the top right. So this is 5 times 5, which is just 25 volts. So now we have a light bulb operating at a DC voltage of 120 volts. So that's our V. It has a power rating of 60 watts. So this is our P. How much current is flowing through this bulb? So we use our top equation. Let's see, we have a V, we have a P. We're interested in current, which is I. So we can use this equation here. P equals VI. Since we want current by itself, we divide by the voltage on both sides. We get power over voltage is equal to current. Power, let's see, is 60. Voltage is 120. So we get 60 over 120. And then that should be 0.5. This next question is a more conceptual question. We have 4 unequal resistors connected in series. That's a key piece of information with each other. Which of the following statements is correct about this combination? And then all of these options, all of these statements are asking about the equivalent resistance. So the equivalent resistance for a series, I've already written it down here. It's just the resistance of each individual resistor added up. So let's go through them. Equivalent resistance is more than the largest resistance. We know that this is true because let's say that they're all 1 except for one of them, which is 2. So we have 1, 1, 1, and 2, and then these are our 4 unequal resistors. Or I guess these 3 are equal. So let's say instead that we have 1, 2, 3, and 4. There, now they're all unequal. So our largest one is 4, but if we do 1 plus 2 plus 3 plus 4, that is 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, and 10 is greater than 4. So we know that equivalent resistance is more than the largest resistance. For our next question, we have a 100 watt light bulb and a 50 watt light bulb. We're devising a circuit that places them in series, and it has a normal household voltage. If each one has fixed resistance, which statement about these bulbs is correct? And it gives us a series of statements. So all of these statements are wondering which one glows more brightly. In other words, it's asking which one of them dissipates more power. The more power dissipated by a light bulb, the brighter it will glow. So we need to calculate the power. We're given the resistance, we're given the power, we're looking for the resistance, and it's a normal household voltage. So I'm gonna choose our voltage to be 120, that's standard. So for power, we have P equals V squared over R. So if we want R by itself, you would multiply both sides by R and then divide both sides by P. So R equals V squared over power for each of these. So R1, I'm gonna say that this is light bulb 1, this is light bulb 2. R1 has 120 squared over 100, which, let me plug that into the calculator. 120 times 120 is 14,400. Divided by 100 is 144. And that is ohms. And then for R2, we have 120 squared over 100. And then I believe that is just it's not over 100, it's over 50. So it should just be multiplied by 2, but I'll double check. 120 times 120 is 14,400. Divided by 50 is, 288 ohms. So we have the resistance now, and we want to know which one glows brighter. And the bulb that is going to glow brighter is actually just the one that has the greater resistance, because we're concerned with a series here. In a series, current remains the same. So if we have power equals I squared times R, current remains the same throughout the whole circuit. So the only thing that changes is resistance. So the greater resistance, the greater the power. So the correct answer is that R2 here, which is 288, is greater than 144. So our 50 watt bulb is going to glow more brightly than the 100 watt bulb. This next question gives us a circuit. It asks, what is the equivalent resistance between points A and B of the network shown in the figure? So to break this up, we have kind of two different things going on here. We have this one resistor here that is 12 ohms, And then we have a resistor here that is in parallel with the two resistors here. So I'm going to say we have 12 ohms over here, and I'm going to say that this is resistor 1. And then we have 6 ohms, which is in parallel with these two other resistors, which is 4 ohms plus 8 ohms, which is 12 ohms. So the first thing to do is to find out the total resistance of the parallel thing happening here. So we use our equation or equivalent resistance in parallel. We get 1 over 6 plus 1 over 12 equals 1 over our total. This can be simplified to be 2/12 plus 1/12 equals 1 over our total. So then we have 3/12 equals 1 over our total. So then we can just invert both of them to get our R total for the resistors in parallel equals 12 over 3, which equals 4 ohms. So what happens is that this box that has the parallel resistors can now be imagined as just one resistor that has 4 ohms of resistance. So now we have our 12 ohm resistor and our 4 ohm resistor, and we just have to add them together, and that gives us a total equivalent resistance of 16 ohms. This can be done because this 12 ohm resistor here is now in series with the equivalent resistance of the whole parallel thing happening here. The next question asks us, which direction do both the conventional current and the electrons in this circuit flow? And it gives us just a basic circuit. So this is again just a conceptual question. Conventionally, current flows from positive potential, or from higher potential to lower potential. The higher potential is going to be higher over here on the positive node of the battery. So current is going to flow this way from positive to negative. I'm going to label that I. However, the electrons, if you think about it, this over here on the right is the negative node of the battery. Electrons naturally have a negative charge, so they're going to repel away from that negative node. So they're going to flow the opposite direction here. Say that these are the electrons E. So the conventional current flows counterclockwise, and the electrons in this circuit flow clockwise. And this will be true for any circuit that you deal with. Electrons are always going to flow away from the negative node of the battery, and conventional current is always going to flow away from the positive node of the battery. So now we have a diagram, and it's asking us which meter is not connected correctly. It may be a little bit difficult to see. I'll try and zoom in here. But 1 and 2, these are both ammeters. And then 3 and 4 are both voltmeters. So the key thing to remember is that ammeters have to be connected in series with whatever they're trying to measure. So I'm going to go A equals series. And voltmeters have to be connected in parallel. Say V equals parallel. So let's just go through. Let's choose each one. We have option 1 here. This looks like it's connected in series, with the whole circuit actually. So 1 is good. Let's check. I guess we'll check number 3 because that's the next down. So this is a voltmeter, so it has to be connected in parallel. It looks like it's connected in parallel with this resistor here, so that one's good. And then we have 2 here. This is an ammeter, and it's connected in series with this resistor here, so 2 is also good. Finally, we have 4. 4 is connected in in series with this here. Since it is a voltmeter, it has to be connected in parallel, and it is connected in series, so 4 is not connected correctly. This next question is going to get a little more into the nitty-gritty of resistors and circuits. We have a number of identical 7 ohm resistors. That's a key piece of information there. Set up as described in the diagram. What is the total resistance of the circuit rounded to the nearest ohm? So before anything, I'm going to kind of break these up into different loops. We've got a loop here with R1 and R2. And then once that loop is completed, R1 and R2 will just be, you can just consider it as one resistor. And so these two are going to be in series, and these two are going to be in series. Once that happens, we'll have 2 resistors, you can consider that. And then those will all be in parallel with each other. And then once we have that in parallel, everything will be all together, and we can finally connect it with 3 resistors all in a line. That may sound a little confusing, but we're going to walk through it, and I think it'll all make sense. So let's start with our R1 and R2. So using the equation for equivalent resistance for series, we have, this is parallel. We have 1 over R1 plus 1 over R2. So I'm just going to use 1 over R, and because we know that they're all equal, so all of my things I'm just going to refer to as R. So we have 1 over R plus 1 over R equals 1 over R total. These two share a common denominator, and so we just add the numerators, and we get 2 over R equals 1 over R total. So we can invert both of these, and we know that our R total is equal to R over 2. And this is for this first loop here. So I'm going to say that this is R over 2. After this, we have essentially 2 resistors. We have one resistor that has a value of R over 2. That's the combined R1 and R2. And then R4 directly below it has a value of just R. And again, remember that our R is equal to 7. And I'm just using the term R so that our numbers are a little nicer. We're not working with 7, instead we're just working with 1. So since these are connected now in series, we just do R over 2 plus R equals R total. So we have R over 2 plus R equals R total. This is the same as doing R over 2 plus 2R over 2, and this equals 3R over 2. So I'm going to say that these two combine to be 3R over 2. And then we have R3 and R5 over here. Both of these have a value of just R, so I'm just going to combine them. R plus R is just 2R. So now we have 3R over 2 and 2R that are connected in parallel with each other. So we invert both of them. Inverting 3R over 2 would give us 2 over 3R. Inverting 2R would give us 1 over 2R. And then this is going to be 1 over R total for this whole big loop here, because there aren't any more resistors left. Common denominator between 3R and 2R is 6. So we get 4 over 6R plus 3 over 6R. This is going to be 7 over 6R. And then remember, this is 1 over R total for our part of the circuit there. So we invert both of them, and we get that our R total equals 6 over 7R. Or no, I'm sorry, 6R over 7. There, that's a little better. So 6R over 7 is the R total for kind of this whole region that I'm scribbling on right here. So now we have 6R over 7, and it is connected in series with R6 and R7, both of which have a value of just R. So if we remember now that R actually equals 7 ohms, we can plug this in. We get our total R for the whole system equals 6 times 7 divided by 7. So that's 6 plus R6 has a value of just 7 plus R7, which has a value of 7. And then this just equals 20 ohms. So we have a problem here now. What will happen to the brightness of the bulb in this circuit if the resistance of R2 is increased and R1 remains constant? And the bulb is right here. We're wondering about the brightness of the bulb, so we're concerned mostly with the power. And then we have resistances and we have some current going through it. So the one I'm going to use is P equals I squared R. So if the resistance increases, the brightness of the bulb will decrease. And the reason for this is because the current is also going to decrease, according to Ohm's law, which is V equals IR. The voltage can't change because the battery has a set potential difference, so the voltage remains the same. If the resistance increases, so like let's say that R becomes 2R, and now we have V equals I 2R. In order for this to be equal to our initial equation, which was just IR, I would have to be divided by 2. So if resistance increases by a factor of 2, the current is going to have to decrease by a factor of 2. The reason that this is true is because these resistors are all connected in series with one another. If they were connected in parallel, things would be a little bit different. But because they're connected in series, as the brightness of the bulb, or as the resistance increases, the current decreases. And with our power equation here, current is squared, whereas resistance isn't raised to any power. I guess it's raised to the power of 1. So resistance increases and current is going to decrease significantly as resistance increases. So our overall power is going to be less and the brightness of the bulb is going to decrease. For our next question, we kind of have the exact opposite effect. We have for the following circuit, if a resistor is added in parallel with R1, so our new circuit would be, here's R1. Sorry, this is going to be a really bad circuit. Here's our R1, here's our, we'll call it R4, and then these are connected in parallel with R2. And then all of these are going to run through and connect to R3. There we go. So we have a resistor added in parallel with R1. That's our resistor is R4. What happens to the current delivered by the battery? So let's talk about what happens exactly right here when we add a resistor. Initially, our resistance was just R1. But now, our total resistance for this section here is going to be 1 over R4 plus 1 over R1 equals 1 over R total. For simplicity's sake, I'd like to show you the math behind this. Let's say that R1 is equal to 2 ohms, which equals R4. We'll say that they're equal. So if we have 1 over 2 plus 1 over 2, that is going to equal, So we have 1 over 2, that's our R4, and then we have 1 over 2, and then this is going to equal 1 over R total. We know that 1/2 plus 1/2 makes a whole, and so we have 1 equals 1 over R total, or in other words, R total equals 1. This is less than our initial value of R1 equals 2. So because of that, the total resistance is going to decrease. So if we go back to our Ohm's law and say that V equals IR, if the resistance decreases, voltage can't change, voltage has to remain the same, it's just a property of the battery. The current has to increase to match that. If you were to half the resistance, current would be doubled to make up the difference. So the answer is that the current delivered by the battery will increase. So for this problem here, we have 5 identical resistors, a battery, and a switch. So there's 2 loops that this is going to follow. It's going to follow this here. And then since the switch is open, no current is going to flow through it. So it is only going to follow this here. So the question is asking which resistors have the least current flowing through them. What happens with the current, I'm actually going to get rid of these loops to make it more easy to see, is we have the current here, which is equal to the current here, which is equal to the current here, which is equal to the current here. Basically, the current that happens before R1 is the same as the current after R1, and the current right before R5 is the current right after R5. This is because when we drew our 2 loops, they split and then they joined up again right before R5. So we have some current that's going to go down here through R2 and some current that's going to go over here. The amount of current is going to split evenly between R2 and over here between R3 and R4. So R3 and R4 essentially have to share that amount of current. And if you wanted to, you can use the R equivalent parallel things to prove that in Ohm's law. I do it in a later problem, so I'm not going to go into it here. But the answer is that R3 and R4 have the same amount of current flowing through them, and that current is less than the current going through all of the other ones. R1 and R2 are going to be equal, and then R2 is going to be equal to R3 plus R4. So this means that R3 and R4 have to be less than R2. And R2 is less than R1 and R5 because it splits right before it gets to R2. Okay, last question here. We have circuits R1 through 4, and they're all light bulbs with a resistance of 2 ohms. The battery has a voltage of 12 volts. I'll write a little 12 next to this. Use the diagram to answer the following question. Which bulb is the brightest? So the key thing to realize here is, again, we have kind of 2 loops going on. We've got R1 passing through R2 here, and then we have R1 passing through R3 and 4 here. So R2 is connected in parallel with R3 and R4, and R1 is connected in series with these. So the first thing we need to do is we need to find the total resistance of the system. So let's first talk about the parallel. We've got 1 over R2, which is just 2 plus, and then R3 and R4 are in series with each other, so they're going to combine. 2 plus 2 is 4, and then that's in parallel with R2, so we have plus 1 over 4 equals 1 over R total. This can be 2 over 4 plus 1 over 4 equals 1 over R total. And then this is just 3/4 equals 1 over R total. So when we invert them both, R total equals 4/3 ohms. Then this combines with R1, which we already know is 2 ohms. So let's find a common denominator. 2 ohms would be, let's see, with 3, that would be 6/3. So we have 6/3 plus 4/3 equals, and then remember this here is our R1, and then this here is our R equivalent from the parallel here. So 6 plus 4 equals 10/3 ohm. So we have the total resistance of the system now, and we can use that to find the total current of the system. Because remember that even though current might be different in the different branches of the system, so between R2, R3, and R4, current is always going to be the same, like right here and right here. A good general rule of thumb to remember is that current is always the same right after and right before the battery. So for our current, we have V equals IR. We have our voltage is 12. We have our R we found to be 10/3 ohm. So we just do V divided by R equals I. So this is 12 divided by 10 thirds, which is, I'm going to do decimals. So that's 12 divided by 10 times 3 should be 3.6 amps. So we have now the total current amongst the system. The next step is to find the voltage drop across each of these resistors. Key thing to realize is that right before R1, so right here, and right after R1, the current remains the same. So we can just use V equals IR to determine the voltage drop there. So we want our voltage drop V, and it's going to equal our current, 3.6 amps, times our resistance at of the R1, which is 2, and that equals 7.2 volts, and that drops across R1. We can actually answer the question right here, though I am going to go through the rest of the question, but we want to know what bulb burns the brightest. And the brightest bulb is going to have the highest voltage. You can see that with power equals voltage squared divided by R, up in the top left here. Voltage squared is going to be a much bigger answer than R, so like 7.2 squared over R is going to be a lot bigger than anything else. But I am going to go through the rest of the problem and prove that. So we know that we have 7.2, we drop 7.2 volts across R1. So that means that from our initial 12 volts, we have 12 volts minus 7.2 is 4.8 volts remaining. And then these volts are going to distribute evenly between the two branches that go R2 and R3 and R4. So we're going to have some to R2 and some to R3 and R4. I'll go over that. So if you wanted to find, like, the way that I'm going to go over this is I'm going to find the current through R2 and through R3 and R4. We know the total current. I'm going to find the overall, or the current through each individual resistor. And I'm going to use the equation. Once again, we'll use V equals IR. So this means that our I equals V over R. For R2, R is just 2 because it's just the only resistor, and our voltage is 4.8. So we have 4.8 divided by 2, which is 2.4. For R3 and R4, they're going to add together. And we're going to end up with 4.8 divided by 4, which is 1.2. So we can see now this is I2, this is I3 and I4, and then earlier we found that this is the current of resistor 1. So I just associated the 1, the 2, the 3, and the 4 with their associated resistors. So we can see that resistor 1 has the most current flowing through it with 3.6 amps. If we look at our equation for power, we have I squared times R. So even with, like, let's take this bottom one is 4. It has the most resistance. This is R3 plus R4. I is only 1.2. And so that number is not going to be very big. But for resistor 1, I is 3.6 amps. So even though the resistance is only 2, 3.6 squared times 2 is going to be a lot bigger. I'll even calculate it out for you. 3.6 times 3.6 is 12.96. And then times 2 is going to be roughly 26. And then if we were to do the bottom one, which is 1.2 times 1.2 it's only 1.44. and then times 4 is roughly 6. And you could do it for the other one if you wanted. We can see now that R1 is certainly going to burn the brightest because it is going to dissipate the most power because it has the most current running through it.